Hi students, welcome to today's class. I know it's a Saturday, okay, because we're having this class because your class is slightly a little bit behind the other class, so I want to make up for the class, okay? So if you're here, please, as usual, can you type your name and your class in the comment box so that it's for my own reference. I will know who has followed my lesson, okay? So please remember to write in your name, put in the comments, okay? And any problem with the audio? Are you able to hear me? Okay. And my class will take not more than 1 hour. Okay, all of them will definitely be less than an hour. Hopefully, I can finish it before 1 hour. Okay, so that you can enjoy the rest of the day. Okay. Please remember to put your names there. Okay, I shall start the lesson. I'm going to share screen. Okay. Okay, I hope that you can see this. I think I can see it, so I think it's no problem. Right. Now, actually, your class has done a little bit about the transport of water. Okay. We have not finished it actually. So actually, I'm trying to go through a little bit, just go back to the beginning a little bit, of course, more briefly, so that you can recall. So there's going to be a continuity. Now, how does water get transported in a plant? Okay, what is the system here? How is water able to be transported from the root up to the stem and finally to the leaves to be evaporated? So actually, it doesn't matter how tall the tree is. Okay, it can be 100 meters tall. Okay, which is the tallest tree in the whole world, which is called this one called sequoia tree, which is found in California. So it is able to pull up the water until to the very top. So it doesn't matter how tall the tree is, this force of pulling the water up is strong enough. Okay, it's strong enough for a short tree, it's also strong enough for a tall tree. Okay, now let's look at the three very important factors that allow the water to be pulled up or to be sucked up until it goes to the leaves are these three. So you need to remember the root pressure, capillary action, and also transpirational pull. Okay, for your class, I have done root pressure and capillary action, but I'm going to repeat just a little bit so that you can remember. All right, okay. Now, is there any problem? Please just just let me check the message. All right, anyone has messaged me or anything? All right. Okay, so I think there's no problem here. I may continue the class. Okay, first of all, root pressure comes from, of course, as you know, it's from the roots. Okay, from the root. So it's because of the root is the organ to absorb water. Okay. All right. Sophia, can you write your name here so that I know who you are? I think I know your English name. I do not know what is your name in the name list. Okay, please write your full name here. Okay, let me go through here. If you look at textbook, here is already labeled three types of the forces. Okay, first of all, I'm going to start from the bottom. Okay, root pressure. Now, root pressure is because of water moving in from the soil into the root, and this is actually through the process called osmosis. So your water that is in the soil must always have a higher water potential. That means less salt, less mineral salt, but more water, okay, compared to the cell in the roots. Okay, so now root pressure is the movement of water from the soil, which is outside the root, outside in the soil, into the xylem vessel through the process called osmosis. Okay, so we look at the first one first. Okay, the second one is capillary action, which is actually talking about water moving up the stem. So the first one is in the roots. Okay, that is root pressure. After the water comes into the roots, it's going to be transported up, isn't it? So that you have the stem. So that action that pulls the water up is actually called capillary action. So actually water pull water, okay, is because of the two forces we call cohesion and adhesion. Later on, look at it, okay. And then lastly, when it goes to the leaves, so this one, the number 3 here is at the leaves. We call it transpirational pull. This is a pull that is actually very strong. It is like a suction because the water disappears from the leaves due to transpiration. Okay, remember when the sunlight is very, very warm, a very hot day, you find that the water will evaporate very easily from the leaves. So because the water is gone, water is gone from the leaves, so it actually produces like a low pressure up here, okay, in the leaves, and it causes the water to be sucked up to replace the water that is lost. So imagine this is the leaf. So when there's less water here, all right, the water from the stem will be pulled up to replace the water that is lost. So in the end, you will find all these three forces come into play in order to pull the water up from the roots, up to the stem, and up to the shoots. So all three must be mentioned. So this is actually a popular question in the essay part. In essay part, when they ask you, okay, explain or describe the process which causes the water to be transported from the root to the leaves, or to the stem and also to the leaves. So you have to explain all three. When you talk about root, you must explain the root pressure. And because it's going through the stem, you must talk about capillarity. And then if it goes to the leaves, you must talk about transpirational pull. So all three, okay, that can easily give you about 8 marks or 8 to 10 marks for your essay. Okay, now let's look at each one of them. First of all, look at root pressure. Now, root pressure is actually here. You will see that when you do a simple experiment, after I show this experiment in the textbook, it explains the water actually moves in from the soil into the root hair. Okay, so now why is because of the difference in concentration. Okay, as you know, you learn in Form 4, when you put fertilizer in the ground for the plant, you must not be putting too high concentration of fertilizer. Okay, do you know why? What happens if you put a fertilizer that is too high concentrated? That means 太浓, too concentrated. When you put fertilizer that is too concentrated, that means your soil here, this water here, soil water will become hypertonic condition, correct? Hypertonic means it's a lot of salt here, but less water. And then if you compare to inside the cell, the root hair cell, so this one will be hypotonic. Hypotonic means the water is a lot, but less mineral salt, less mineral. Okay, it's hypotonic in the root hair. And this condition should never happen. Okay, if you have a condition where outside the plant, that means in the soil, it's very nong, that means a lot of salt content is too hypertonic. What happens is the water from inside your root, which is your plant, will move out. So your water will be lost. Okay, water will be pushed out, and then ultimately you find your plant will dry up and it's going to wilt first. Then later on, we do not put water back, you do not replace the water, it's going to die. Okay, so your plant gets dehydrated. So this thing should not be able to happen. So what happens is naturally your soil must have more water compared to the root hair. Okay, so I rub this away first. So this is not a good condition. You should not have the soil hypertonic, but you should have the soil hypotonic. Okay, hypo means high water potential. Okay, high water potential. So here should be hypotonic. Hypotonic means a lot of water. Water is concentrate. The water molecule is a lot, but the salt is little. Okay, hypotonic. And inside your root hair, it should be hypertonic condition. Okay, this is what should happen. All right. Let's look at the explanation here. Number one, this whole thing explains the root pressure. Now let's see it. Look here. The number one, the water potential in the root hair cells is lower. So it's talking about the root hair cells. So inside here should be less water. So we call it low water potential. Okay, here should be low water potential. Low water potential means they got more salt inside. Low water potential, 比较少水. Okay, that means this is a hypertonic condition. All right, hypertonic means more salt, less water. So it's low water potential. Compared to the soil water, okay, this is a wood hair I'm drawing here. This is the soil. This is the water outside here. This is the soil. Okay, so the condition in the soil should be hypotonic. That means here should be more water. compared to inside the root hair. So this one is high water potential. This is a very healthy condition now. Okay, the soil water should have high water potential. Okay, so jot this down as you are following the lesson. Right, the picture here showing a root hair. So water is hypotonic. All right, the soil water is hypotonic. The cell is hypertonic. Okay, now let's look here. The water potential in the root hair is lower. So you see low water potential compared to the water in the soil. This is because, now why is it like that? The mineral ions are actively pumped by the root hair cells into the vacuole. So this root hair actually is getting in minerals. Okay, it will pump in ions. Ion is the salt lah. So when it pump in ion here, it will be more salt inside the cell. That means it's going to be hypertonic. So the cell here will actually pump in mineral salt. Okay, this is through active transport. Okay, so causing the cell sap of the root hair to have low water potential. So the cell here will have low water potential. That means here less water, outside more water. Okay, so number 2, first of all, you must mention the condition. First point, you mention inside, outside. Inside is how. Outside the cell is how. Okay, first point, you mentioned that. Secondly, because of this condition, so you will find that the water in the soil or from the soil will diffuse into the root. So water automatically comes in. Okay, through the epidermal cells, through this process called osmosis, which you learn in Form 4. So water goes in. So when water goes in, all right, now the high water potential, so this cell now becomes high water potential already because water has come in. Now water has come in, so this one no longer low water potential. It's going to be high water potential already because water has already come in. So, all right, no longer hypertonic now because water come in. Okay, the high water potential in the root hair cells causes the water to diffuse from the root hair cells into the cortex via osmosis. So the next cell, you must talk about the next cell. So this is the root hair cell only. This is the first one. This is the root hair cell, right? Number 2 here. Now we're talking about the inner part. After the epidermis, you have the cortex. Now this one, comparatively, it will be hypertonic. Okay, because less water. So here water has moved into the cell here, number 2 here. So now because of the difference in the concentration of water, in the cortex is is a low water potential. Epidermis cell or the root hair cell is high water. So again, now this water is going to be transferred to the next part. So it's like go in already, the water will be continuously transferred to the next cell. So once the water enter here, now this one is no longer hypertonic. Now it becomes hypotonic compared to the neighbor cells, compared to this cell. This is hyper now. So again, this water is going to be transferred in. So it's like one by one, okay? Water will be transferred from this cell to another cell, to another cell, to another cell, because the ones that are inside is always hypertonic to the ones that is already water come in. Okay, so here, number 3 done already. Now number 4, this condition, that means the difference, one cell is hypertonic, one cell is hypotonic, causes osmosis to continuously occur. From this cell, cell 1 pass to cell 2, cell 2 pass to cell 3, cell 3 pass to cell 4. So the water gradually gets transferred inside, okay, through the cortex. Cortex is thick lah, all right? So a few layers of cells. So this one goes through the cortex, then continuously through the endodermis and also to the pericycle. So after the endodermis is the pericycle. Okay, endodermis is, you remember there's one layer of what we call Casparian strip. Okay, after I show you. So this slowly you find the water will be transferred from one cell to one cell to one cell to one cell. Later on, it goes into the xylem. Then the water gets pushed up the xylem. And later on, you will have the second force, which is the capillary action. How water goes up the xylem is the second one. The first one talking about root pressure is coming from the soil into the root here. This is called root pressure, okay? Because outside is hypotonic, the cell inside here is hypertonic, so water keeps on moving in. Okay, so this causes root pressure. Okay, sorry, the root pressure. Any problem so far? Any questions here? Let me just have a look. Okay, nothing, just names only. Okay, so you can see here. Sorry. So this is what just now, all these words, okay, same thing here. So this is an experiment to show there is wood pressure. You will take a tree, of course you have to sacrifice a tree, yeah? You cut it very near to the base. Of course, you need to water it very well. You need to water the plant first, right? Sorry, you put water there. And of course, it has to be a tree that is herbaceous, because it's easier to cut. Then when you cut away the whole tree, the stem, you find that the water will ooze out. It will not, like a fountain, it will not punch, it will not shoot out because the pressure is not very high. It will just ooze out. Ooze out means 流出来. You can see that after the place that is cut is going to be wet. So this shows that there is wood pressure. So water is actually pushing up. Okay? But this is not going to be very strong. It is going to be maybe just a few cm or a few inches off the ground, off the root only. Okay, that is the first force. Okay, understand? Excuse me. Okay. So now we're talking about the second one. The second one is how does water transfer inside the xylem itself? Inside the xylem itself. So here, we talk about the second one, which is capillary action. So now the water has come in. Now we're talking about here already. The water has come in here. Okay, how does it go up now? So this one has to do with a force inside the water molecule. So inside, in between. So here you find if there's a water molecule, of course H2O, one oxygen, and two, H2O, isn't it? Yeah, one oxygen, two hydrogen. Okay, so this is oxygen, this is hydrogen molecules. The atoms. This is one molecule of water. In between one molecule of water and another molecule of water, there is actually a force. There is a attractive force. And this attractive force, I'm going to draw it the other way around. Okay, like this. Okay, always remember your Mickey Mouse, Mickey Mouse, the shape. So this one is oxygen, this is going to be hydrogen. There is an attraction here between the oxygen and the hydrogen because they have opposing charges. Okay, oxygen is slightly negatively charged, hydrogen is slightly positively. The charge will be more accumulated towards the positive charge, will be accumulated towards the hydrogen side. So this force, all right, in between the molecules here, this force is called adhesion. This is the force that exists between the molecules of water. Sorry. This is called cohesion. I'm so sorry. Cohesion. Cohesion. Cohesion is the force. This is the name of the force in between the molecule of water. This will try to make the water actually stick together. As you know, it's quite difficult for you to cut water. All right, you cut water, you join back, isn't it? It's not easy to cut water. In fact, you can't cut water at all. You cut, you put scissors, you put knife, you cut, you find the water will join back together. This is because of the cohesion force. Water will pull water. Water will 黏 water 的. Okay, that force is called cohesion. So this one is one of the forces called cohesion. Now another one is called adhesion. Adhesion is the force that is between the water molecule and the wall. The whatever wall it is, it could be the beaker, it could be the xylem wall. This force is in between the water molecule and the site. Whatever beaker or container is holding it. Okay? Understand? So there are two forces at work here. One is cohesion is between the water molecule itself. Cohesion is between the water molecule and the wall that holds the water. So in this case, it's the wall of xylem. So that you will see that water, when it touches the site, it will try to stick to the site. So when you see in the beaker, I'm just explaining that day when you had the class. So when you have put water in the beaker, you find the water will never be flat. Towards the end here, you will see the water will curve up. Okay, slightly curved. If I magnify, you'll see it's slightly curved. This is because when you look at water molecules, let me magnify it. Now this is a cohesion. Cohesion between water molecule. I don't show the hydrogen. I'm just showing the oxygen. I'm just showing the oxygen. I'm not showing hydrogen. So here, your water will be pulled to the wall. So you see this one, the one that's nearest to the wall, it will be pulled up. So you see that's why you can see there's a curve here. There's going to be a curve. So this is the adhesion force. So whenever you have a water in a tube, let's talk about tube or straw or anything, the water will always try to stick to the side, and at the same time, the water that is already there will pull the other waters along. So it's like water pull water. That means your water will always stay in the tube, in the whatever, straw, whatever. It's not easy for the water to break up inside there. So you have a continuous stream of water. It's because 水拉水, water pull water, water pull water. So when the first one goes up, the second one will still follow. So that means water will be easily sucked up. Okay, so this action of having cohesion and adhesion causes this force called this phenomenon is called capillary action. Capillary action is the ability of water to be able to be pulled up in a tube, and it's not going to break up. Okay, so this is capillary action. Capillary action is caused by the two forces. You have adhesion and cohesion. So 水拉水, okay, water pull water, and water also be pulled to the side here. So it's not going to drop. Water is not easy to drop. Even though you find that the pressure of the water, the plant is very tall, it's not easy for the water to would drop down. Okay, because of the high tension and also because of the forces here. Okay, so let's look at the words here. Now, the continuous upward movement of water through the xylem. Now, this is movement through xylem. So when you talk about movement of xylem, it might be capillary action. Just now, the movement from outside, the what you call the soil into the root is called root pressure. Now, when you talk about going up in the stem, okay, in the xylem, you must talk about the second one already. This is called capillary action. So this is attributed to, that means it's caused by adhesion, the forces between the molecule, forces of attraction between different molecules, not different molecules. Means the molecule of water and the wall. And cohesion is between the same molecules. Okay, and then you see that, look at here, capillary action causes the water to be filled up in a tube. And you can see the thinner the tube is, the narrower the diameter, it actually supports a taller column of water. Okay, the finer the capillary is, the suction is actually better. So imagine the xylem is actually very thin. The xylem is very thin. So the water actually can be pulled up very high. Okay, so this prevents breakage. The cohesion factor, the cohesion force actually doesn't make the water break up. So water will be always in continuous. It prevents breakage. Okay, so this causes the water to be continuously pulled up. Okay, right. So that is the second one. So here, water molecules adhere or stick to one another by cohesive forces. If you don't want to use the cohesive forces, it means cohesion. It's the same thing. If you don't want to use cohesion, you can say cohesive forces. It's the same. So same thing for adhesion. Adhesion means adhesive forces. So of course, better use one word, isn't it? Better why use two words? Better use one word. One word is called cohesion. The other word is called adhesion. Okay, so the water molecules adhere, that means stick to the walls, and this is by adhesive forces. So this is due to hydrogen bonding. Okay, the bond between the hydrogen and oxygen there, because of different charges, is hydrogen bonding. So xylem vessels are very long, very narrow. So when you have very, very narrow, they will form a continuous tube here. And the more narrower the diameter of the xylem, the better it is, the force will be even stronger. That means it's going to be sucked up very, very high. Okay, so this is the capillary action is the result of these two forces that enables water to enter and move along very narrow columns and to be pulled up, okay, up to a few meters, not only half a meter. I think it is, of course, not as strong as the third one. Okay, so first one is the weakest. The root pressure is only, you can only see towards when the root is here around few inches off the ground. You cut off, you can still see the water oozing out. That is the root pressure, not very strong. It's not going to push up all the way there. But in your capillary action is a bit stronger. It can pull up to about a few feet or a few meters. And then the third one is the strongest, which is the the transpirational pull. Okay, so we're going to talk about the transpirational pull now. Okay, that one. I think for your class 5S4, we stop there. Okay, now, before we talk about the transpirational pool, there's one part I want to tell you also, which I've already missed out last time. Now, how does water move from the root into the xylem? Okay, you see here, this is a cross section. This is the root, right? Where you can see the root hair and it's cut through. Now you magnify here. Remember, we learned about this Casparian strip. Okay, Casparian strip, it is a material that is in the epidermis here, which is actually waterproof. It does not allow the water to pass through. Okay, now let's see how does water move in. When water goes into osmosis, of course, okay, don't forget it's osmosis, because here is what? In the soil here is high water potential in the soil, TIAL. Okay, sorry, what is this? Somebody has mentioned something here. Oh, very interesting. Okay, right. High water potential. So in the water, the soil water has always have higher water potential compared to in the cell. Okay, so now water moves in through the root hair. So here, imagine water has come in here. Now, once water has come in here, of course, here, like you said, this becomes more water. That means it becomes hypotonic already. Now, let's see how it moves. First of all, water can be transported in two ways through the root. We're talking about the root now. There are two ways. These two pathways have a name. So this, look at the name, Symplast pathway and Apoplast pathway. Okay, there are two ways where water moves in through the root. Now we're talking about the root only, not talking about the stem. Okay, root. First one is called Symplast. Symplast means this pathway, this jalan, the root, the pathway. The water moves through the cytoplasm and plasmodesmata. Cytoplasm is inside the cell, of course. So this is cytoplasm. What I draw here is all the cytoplasm. This is cytoplasm. What is plasmodesmata? Plasmodesmata is this one. You will see that there is a connection. There's something like a space here, an opening in between. This is the cell wall and the cell wall of the two cells, right? This is a cell wall, this is a cell wall. There's an opening here in between here to allow things to pass through. That opening there is called plasmodesmata. So I put label here, green color. See that? Too dark. Okay, so maybe I circle it. Red. You see it here? This is plasmodesmata. In between the root hair and root hair, in between the cell of the root and the cell of the root, you have a little hole there which allows transport of substances. So that's called plasmodesmata. So now this water moves across through the what they call the through the cytoplasm, and also it passes through the plasmodesmata. That is the Symplast. That means it moves into the cytoplasm. Now the other second one is called Apoplast. Apoplast, for Apoplast pathway, the water moves through the spaces between the cellulose fibers at the cell wall. It doesn't go into the cell. It goes, you know, where is the cell wall? Okay, let's look at this is a box. This is a cell. Let's say this is the whole cell. The cell wall is only covering the outside, isn't it? So it actually goes along the cell wall. So it means it doesn't go inside the cell. Now you can see the color here is the red color label. This one, Apoplast. Apoplast, it goes through the cell wall. You see? It goes through the cell wall only. It doesn't enter the cytoplasm of the cell. So this Apoplast is passing through the cell wall only. So if you look at the picture here I've drawn here, the green part here shows the cellulose component of the cell wall. Okay, so if water were to pass through into the Apoplast pathway, okay, anything here? Okay, okay, so I'm going to show you with a blue arrow to show the path of water. So blue color, okay, blue color. So let's say water is passing. Okay, water. This is water, water trying to move through. Okay, this is all water. Now there are two ways, right? The first one is through. So we mentioned Symplast. Now Symplast is going through the here. It goes directly through the what? The cytoplasm. Then the white part here is the cytoplasm. The green part is the cell wall. So cytoplasm, of course, I didn't draw the nucleus and all that. Okay, let me draw nucleus. So let's say this is the nucleus, right? Okay, I have black color. Wait 1 minute. Change the color. Okay, this is the nucleus, and this is the cytoplasm. This is called the what plus? This is the Symplast. Passes through. Now the second one is what? Apoplast. A++ is this one. The water does not go through the cell, the cytoplasm, rather it passes here. It goes through where? It goes through the cell wall. It passes through the cell wall only. That means the outer shell there. Let's say this is the what? It passes through the here, all the outside here, and here. It doesn't go into the cell. Okay? And then what happens is at the endodermis, there is a layer called Casparian strip. So this Casparian strip, I'm going to draw here. I'm going to draw black color. It is going to block already. It can grow until here, but then you see somewhere here got the black color. This is a Casparian strip. It can go halfway only, but then after that block already. You have the Casparian strip already there. It is going to block. So let's say this is the rubber band. This is going to be a Casparian strip. Okay, I'm going to wind it around here. You see my box here. So this is the cytoplasm pathway, which is the syn+. And now the apoplast going through here, 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 and here. You see, it can go here, somewhere here, but you see here, block already. Here's what, this is the rubber band represents the Casparian strip. So now it cannot move in anymore. So what happens? Where's the water going to go? The water will go into the syn+. That means here it's going to be blocked. Okay, from outside, from the endodermis, before the endodermis, it can go through two ways, apoplast and syn+. But when it comes to this endodermis strip, because the Casparian strip will block it already, so it no longer can go through the apoplast pathway. Now this one will go into the cell and it goes in by the cytoplasm. Okay, still the same thing. Whatever it is, you still move into the xylem. Okay, you will still sampai. The only thing is, the advantage here is, why do we have the Casparian strip? It is actually to force the water to go into the cytoplasm. Okay, earlier on, you can still pass through the fibers of the cell wall, can still pass through. But towards to this layer, after that, no more. Cannot pass through already. You have to, the water is forced to pass into the cytoplasm. So in the end, after that, it's all going to go into the xylem vessel. All right, okay. So you remember these two pathways. One is apoplast, one is syn+. In the beginning, you will have outside the endodermis layer, you will have two methods. The water will move in. So afterwards, when it passes through the endodermis, because of the Casparian strip, the water cannot move through the apoplast pathway already, but it will move through the syn+ pathway. Okay, so now we go to the third force, which is called transpirational pull, which is the strongest one that causes water to be able to be sucked up to the plant. No matter how tall the plant is, it will still be able to move up. All right, okay. Now, okay, just put your name there, and so I know that you're there, my students are. All right, so third one, transpirational pull. Now, this has to do with transpiration. You know transpiration, where you have sunlight. When the plant is exposed to sunlight, okay, when the plant is exposed to sunlight, you know water is going to evaporate from the leaves, from the stomata. So let's look at this one. Now, this is the layer of cell. Okay, what I've drawn here, this is the lower epidermis. This is the stoma. Okay, the stoma is the opening here, the pore. And this is the spongy mesophyll. Spongy mesophyll, there's a lot of airspace. And this is the xylem inside here. Xylem. Okay, xylem here, of course, is water lah. This is where the water, the source is going to be here. All right, now how is transpirational pull helping the water to move up to the xylem? Okay, let me look at any... All right, okay, no questions here. Now, first of all, let's look at, as water evaporates from the mesophyll cells to the atmosphere, their cell set becomes hypertonic. Okay, so first of all, it has to be, of course, happening from the transpiration first. When the sunlight is of course shining, it's very warm, it's very hot. So the water from the mesophyll, this one, the spongy mesophyll, the water will evaporate. So the water comes out. Okay, so I rub away this line here. So the water will be evaporated in the form of water vapor, H2O moves up. So that means this cell now is going to be hypertonic because water has gone, water has evaporated. So it's going to be like less water. So as a result, compared to the adjacent cell is a neighboring cell. So let's look at this one. So this is cell number 1. Okay, I put cell number 1 here. This cell number 1. Look at cell number 2. Comparatively, because this water has disappeared, okay, this is going to be more hypertonic now. Compared to the number 2 still have relatively more water, correct? Yes, relatively more water. So that means this is going to be like hypotonic. So here will be higher water potential. The cell number 1 is lower water potential. Okay, let me write down here. Right, this number 1. So now water will be transported from cell number 2 to go to cell number 1. From number 2, move to cell number 1. It's like something like replacing lah. Because number 1, the water has gone away. So it makes it more concentrated. The cell is now hypertonic. So number 2 cell, the cell number 2 here, which has got relatively more water, so the water will move to 2 to 1. So that means like transfer the water from 2 to 1. Okay, now when this water has been transferred from cell 2 to cell 1, now compare to this cell which is near to the xylem. So it looks as if now the cell number 2 would be what? Would be already hypertonic because less water already. So now this is hypertonic. So now compared to the xylem now. Xylem here is like more water, right? High water potential. So water will move in. So it's like 一个传一个. Okay, one transfer to another one, this one transfer to another one. So in the end, when water disappears from the cells in the leaves here, it's actually helping to suck the water up. It's helping the water to move up. So this xylem is going to be, of course, connected to the xylem in the stem. So as a result, the stem, all right, water will be sucked up to replace the water that has been lost. Okay, so it's like, generally speaking, it's like because this one has lost the water, so this water from this side will transfer there. And then when this one has lost the water, so now this one from behind here, the cell here will transfer to here. So it's like, it's like a domino effect, right? One lost the water, so this one transferred to this one. And then this one lost water, so transfer. So in the end, you'll find a continuous flow of water from the xylem to the pores or to the stoma. Okay, water is continuously. That's why transpiration helps actually to pull the water up from the xylem to the leaves. Okay, let's look at the words. Let's look at the words. Okay, so this is what I've actually explained from here. The same diagram here. I just use my own drawing. So the first one is when water evaporates, right? The cell, the mesophyll cell will become hypertonic. That means low water potential. Then water diffuses from the adjacent, that means the nearby cell, the cell number 2, all right? Will diffuse from number 1, or from cell number 2 will diffuse to the cell number 1, to the cell that have lost water. And then now the cell number 2 now lost water already. It will take the water from the xylem, okay? So water from the xylem vessel is then drawn into adjacent mesophyll cells. So now water from xylem goes here. So as the mesophyll cells, something like suck the water, it's considered that it's a pool, because it's sucking the water up, right? The whole column of water is pulled up from the roots to the leaves because of the cohesion and adhesion in the stem, right? The capillary action there. All right, okay? Okay. Right, no questions here so far. Okay, so now water, this force whereby the water disappears from the leaves because of transpiration, it's just like sucking the water up from the stem, okay, from the stem, from the xylem in the stem, so it goes into the leaves. So this pulling force, now look here, this is a pulling force. It's like sucking the water, right? Because it's the water in the leaves are disappearing. Therefore, that's why the water can go in, replace it. So if the thing is, if the water doesn't disappear from the leaves, that means actually the water will not come up. Okay, so transpiration is actually good for the plant. When you have transpiration, it actually, when water disappears from the leaves, it actually helps to suck up the water. And don't forget also minerals. See, all right. So if the water doesn't disappear from the leaves there, that means there's no chance for the mineral to go up the plant. There's no chance for new supply of water to go up the plant. There must be a kind of replacement, because when this one goes off, you have to something to replace it. So that means there's chance for the mineral to move in. Okay, so don't think that transpiration is bad. Transpiration actually has two important effects. Number one is to pull up the water. It helps the water to be absorbed up. Number two, it has a cooling effect. Okay, it is like it uses the heat. All right, when water evaporates, the water needs to absorb heat in order to change from liquid to gas. So it's actually absorbing the heat here and it's dissipating the heat. So the plant will have a cooler, it has a cooling effect. So the temperature of the plant will drop. Okay, so it is better. So this is a two advantages or the good the effects of having transpiration. Number one, help to transport water and minerals. Number two, has a cooling effect. So this force is called transpirational pull, and it's a pulling force. Okay, so the higher the transpiration, the higher the pulling force will be lah. So the water can be pulled up, and doesn't matter how long or how tall the tree is. It can be over 130 meters tall. The force is still very strong because it's not broken in the stem, in the capillary, because of the capillary action. The water is not broken. It will still be continuously until the end here, which is the leaves. Okay, so this is the third force. So when I talk about the three forces here, the strongest is always the transpirational force, followed by the second one is capillary action, and the weakest is the root pressure. But all three are equally important. Okay, if you do not have any one of these, the water will not be able to be transported efficiently. Okay, so now let's look at some experiments to highlight this root pressure and transpirational pull. Okay, understand? Right. Let me look at the, okay, let's look at the things again. Right. Okay, now root pressure. Root pressure can be demonstrated, all right, if you do this experiment. So first of all, the plant has to be well watered. It has to be, you have to put a lot of water there and make sure the plant is not dehydrated. Then you have to water the balsam plant and keep it overnight. Then you cut the stem around 5 centimeters from the base. From the base here, don't cut it too high because you know the root pressure is not very strong. So you cut it at the base here. Then using a rubber tube, right, you connect it. This is the rubber tube. You connect it to a manometer, a U-shape. A manometer is a U-shape one, a U-shaped tube like that. And make sure you put water inside there. Colored liquid also can. Make sure it's level. Then after that, you apply jelly, petroleum jelly here to make sure that it is airtight. It cannot have water. It cannot 老风. 老风, the experiment's not going to work. You must have air going inside. Mark the initial level here. Initial, this is where the water is. Leave it for 30 minutes. Okay, and you will see that because of the root pressure, of course it has to be well watered right? The root pressure will push the water up, and it's going to push a little bit This water level will rise a little bit, just a little bit. Okay, not a lot all right? It goes up a little bit. Understand? All right, so the observation here would be the level of water. You will see that the level will rise after about, let's say, 30 minutes or 1 hour. So because of this demonstrates the root pressure. This demonstrates root pressure. Okay, the second experiment here is to show transpirational pull. So you have to make sure you have water supply here. The plant has to be immersed, the whole root has to be immersed in water. Okay, and of course here is you block out you do not want evaporation to happen from the surface of the water. You want the water to evaporate from the leaves. Therefore, you put a layer of oil here. You want to block it. You do not want the water to evaporate from there. Okay, then you leave it for a few hours, at least 30 minutes would not be able to see the result because transpiration happens quite slowly. Okay, you leave it for, make sure everything is airtight. Okay, you can read the instructions later. Okay, instructions. So here, when water evaporates, this one you've seen in Form 3, Remember 2 years ago, we had something we learned about transpiration. So when water evaporates, the water will disappear from the leaves here, leaving there's going to be some empty space. So the water from the root here and also the stem will transfer up here, or water will be sucked up here, and you'll find this water level will drop. Okay, that is the observation here. The water level in that tube here, okay, you will see that it will drop slowly. Of course, it takes some time. The water will be absorbed up to the leaves. Okay, so this shows transpiration. And you can measure, give a certain amount of time. Rate of transpiration is always measured in terms of how much water is lost. Okay, water loss. Okay, LSS loss as in the noun, divided by time. When you talk about rate, it's always divided by time. So usually it talk about minutes lah. Okay, per minute or per second will be too much lah. Okay, so minute, hour also can. Water loss is how much water that has gone down. So it could be grams, or it could be in terms of here is how many cm, not in grams. You can see the water come down. But this transpiration experiment is quite difficult to do lah. Okay, I give you a video on the Telegram there. You can have a look at how to pasang the thing. It's not easy because once it's water, there's air bubble inside there, then it's very difficult to have that continuity. The water must not break, the column of water inside the tube must not break. Okay, now lastly, all right, let's look at a phenomenon known as guttation. Okay, guttation. Now, not all plants will carry out this guttation. Okay, now first of all, there's a mistake in your textbook. Please add this word. Guttation occurs when the root pressure is high. Okay, this is left, this is omitted here. Root pressure is high. That means there's a lot of pressure coming from the root. It's going to push the water up, and actually it's going to come out through the leaves. So when you see all this little droplets of water at the side of the leaves here, this is the phenomenon called guttation. The water is going to be secreted in the form of water droplets. It's not going to be in water vapor. Water vapor you cannot see. Just like transpiration, you cannot see the transpiration happen. But in guttation, you can see, because you can actually see droplets of water being pushed out through specific places. The specific places is actually at the side of the leaves. At the side there's actually little pores, which are called hydatodes. Okay, so what is this phenomenon first? Guttation is a secretion of water droplets. So remember this word, it's not just water vapor. Water vapor is wrong. It's water droplets through a special structure. This special structure is called hydatodes. At the end of the leaf veins, without involving the stomata, it doesn't go out through the stomata, caused by high root pressure. So it's the root pressure that causes it to happen. That means the water pushes up. So usually this is for small trees, because as you know, root pressure is not very high, very strong. It cannot push up to a tall tree. Usually small shrubs, or especially I can give you an example, is a strawberry plant. Strawberry plant has been known to exhibit guttation. Okay, let's look at this one first. Now, so this is the pores here are called hydatodes. Now, why does guttation happen? Why can't transpiration easily enough? Now, sometimes transpiration cannot happen. The reason here is because the temperature is not high enough. It's too cooling. Okay, or maybe the air is too humid. Okay, a lot of air, we call it the water. The air is very humid. That means a lot of water molecules is in the air. So that means there's no chance for the water to evaporate. Okay, there's no evaporation. But the plant still wants to remove water. Okay, only thing the water cannot evaporate. So the other method to remove the water is through guttation. So the water is going to be actually pushed out through these little holes here called hydatodes. So at night, all right, at night you find that the roots will still continuously to transport water and ions. That means the root, the water will still be pushing into the root here. So that means the root pressure will be high. Okay, so root pressure will increase. So if you do not have a place for this water to go, your xylem could be too high pressure, it could be burst, or the veins can burst, whatever. So, and then when it happens at night, the transpiration rate is low because it is too, what they call, too humid at night, not hot enough. The water, the air, 潮湿 means it's a lot of water molecule in the air. So it's very saturated. The air is very saturated. It cannot happen through transpiration. Okay, so what happens is this root pressure is going to push the water up through the leaves here, and this water will be pushed out at the side here at the little pores there, right? And you're going to have little droplets of water sticking to the side there, and you will think that this is like a dew drop. You think it's a 某水, okay? Sometimes you may think it's a 某水, we call it dew drops. but it may not be moisture. It's actually water pushing out from the root pressure there. Okay, so it usually happens on cool, humid mornings when it's too cold, right? And the water is too wet. There's too much water saturated. The water is very saturated, so it's difficult for the transpiration to take place. Transpiration doesn't take place. So the plant still wants to remove the water. So this is the only way. The water is pushed out and you have droplets of water there. Okay, so now let's compare between guttation and transpiration. Okay, so this point is actually same as the one in the textbook lah. Okay, let's look here. So it usually happens at night and early morning when the air humidity is high. That means the air is very wet. All right, and the surrounding temperature is low. That means it's very cooling. It's not hot enough. The water does not get a chance to change into gas. Okay, it's not warm enough to change into gas. So it will excrete the water in that manner, in that way. Okay, let's compare similarities and differences. When you say comparing, don't forget to talk about similarities as well. So both occur through the leaf, similarities. And both will cause water loss. Okay, you no need to say permanent, so never mind, it's water loss. But only thing is different form. Guttation is droplets of water. The other one, transpiration, is in water vapor. Okay, differences. Guttation happens when, okay, not in the afternoon when it's very hot. In the afternoon, it will be transpiration. But here at night, okay, when it's very cooling, and early morning also when it's very cooling and the humidity is high. For transpiration, it happens on hot and windy days. So in the afternoon, daytime, when it's bright and shiny, you will have transpiration instead. Transpiration is for all the plants. It happens in all plants. But guttation doesn't happen in all the plants because not all plants have this thing called hydrototes. Okay, so they want to remove the water also, you have to wait for transpiration because they don't have the hydrototes. Not all plants carry out guttation. Okay, so guttation only happens in herbaceous plants. Okay, remember, because they're short, if you have very tall trees, your root pressure is not going to be high enough to push the water up until it drops up from the leaves there, the water. So it's only for herbaceous plants, which are non-woody. But for transpiration, it's for all the plants. Okay, as long as you're a plant, you will have transpiration. Okay, number 3, water is released in the form of, now see here, water droplets. You can actually see the water droplets there in liquid form. But for this one, it is water vapor in gaseous form, which you cannot see. It just disappears into the air. Okay, next one, water is released through the special structure. The special structure is known as hydrathodes. Hydrathodes. And for transpiration, it of course happens through the stomata. Okay, next one. Guttation happens when root pressure is high. Yes, okay, that's the only way. When there's no root pressure, is not high enough, it's nothing is going to be pushed out. And transpiration is controlled by the stomata opening. So this is happens because of the water being evaporated from the stomach. And one more difference, guttation releases water that is rich in minerals. So it's not only H2O. Okay, there is mineral dissolved in the water as well. Whereby for transpiration, it's only H2O. Because when it evaporates, the mineral salt doesn't evaporate. The mineral salt is no way it's going to evaporate. It's only water, H2O, pure water that is changed from liquid to gaseous form. Okay, so it's pure water. So these are the points you can talk about. Okay, now what happens if plants cannot undergo guttation? It cannot undergo transpiration. See, like what happens to effects. So if the plants that do not undergo guttation, right? So the effective root pressure cannot be maintained. That means if you do not have guttation, the water doesn't move out from the leaves here, then the root pressure will not, the water will not move in. Okay, like I said, just when the water doesn't disappear from the leaves here, there's no way for the water to move in. Okay, so water absorption by root hair will be disrupted when there's relative high humidity, when there's too wet, when there's too much water in the air, so you cannot have the transpiration. Okay, it will carry out guttation. Now, without guttation, plant waste or substances cannot be eliminated. So this is one way of excreting also. It excretes not only water but also minerals. So if guttation does not occur, the leaf pressure may become very high. Okay, so if there's no way for the water to move out, the pressure inside the leaves, the veins will be high, and it can cause the leaf vein to burst. So burst, that means the cell will rip okay, and the surface of the leaves will be broken, and this can cause bacteria and virus to attack the plant, okay, be exposed to pathogen. So the leaf will be attacked by pathogens. Okay, now what happens if the plant do not undergo transpiration? Of course, the temperature cannot be maintained because remember, I told you earlier, it has a cooling effect. Transpiration has a cooling effect. It actually cools down the temperature of the plant. And if the plant is too high, all right, the temperature too high, the enzymes can denature, and of course, it disrupts the chemical processes, biochemical processes, maybe respiration or photosynthesis will be impaired. That means it does not happen at the correct rate. It's taken too slowly. Okay, without transpiration, also mineral ions cannot be transported. It cannot, number one, cannot go into the root, and the root will not be able to push it up into the plant, into the cells that the plant will not get these minerals. So it helps in water absorption. So without transpiration, water transfer will be disrupted. There's no water entering the cell, and the plants will die. So actually, transpiration is good. Don't think that losing water is bad. There will be a lot of water in the ground. There will be. As long as transpiration, the water in the ground will always be continuously replacing the water that's lost. Unless, of course, we're talking about musim kemarau, which is drought. If it's drought, then you can severely, some of the plants can actually die because the soil, the water in the soil is actually being finished already. But if you have in Malaysia here, we always have, so many, weather is always humid and there's always rain. So usually there's no problem. When you have transpiration, the water will always be replenished, and there's actually a lot of water in the ground. Okay, then the plants can die in the long run when it has diminished the supply of water in the ground, and you do not get replaced by watering the plant. Okay, so here you have the effect of plants that do not undergo guttation and transpiration. So here, this is an important point also, comparing guttation and transpiration. Okay, so this is something to really remember, and also how to explain the three forces. That one is important. This one. Explain the three ways when water are transported from the roots to the stem and up to the leaves here. So this is important. Okay, all right. So any questions here? I've mentioned what I wanted to say. So 5S4, you still have one more class, which I will do another time. Okay? That will be the phytoremediation and also translocation. Okay, yeah, one class behind. I will eventually replace that as well. Okay, so any questions so far, girls? Okay, no questions? No questions, that I will see you again in the next time. I'll see you very soon, actually. Okay, I'll see you very soon in school. Okay, right. So thank you very much for joining. All right, I'll see you another time. Okay, any questions, please put in the Telegram, and I'll be happy to answer your questions. Okay, bye-bye. That's all for now, girls. Bye-bye. See you. Okay, you can watch the replay anytime. Okay, bye.